Thank you for attending my talk on benchmarking low-power wireless networking systems. And let me start off with a brief motivation. So my topic is a bit further removed from the previous speaker. I do have a massive scale, but my problem essentially is the number of devices. So Cisco, the maker of all things internet, essentially periodically gives out their prediction for the number of internet-connected devices, which by 2030 is said to be around 500 billion devices. Of course, these devices are not all servers or smartphones or other conventional computer devices, but many of them will be deeply embedded devices, which include sensors to actually observe the world around us, and of course also actuators to interact with it. And unfortunately, there is a large difference in use cases between those devices. For example, you may have noticed, especially in Europe, there is a looming energy crisis. So utilities companies would like to leverage the smart grid and know which devices, which consumers are using. And instead of essentially rolling blackouts in the middle of winter in Europe, we would like to shed load where it doesn't hurt anyone. Other fields like manufacturing have the rallying cry of Industry 4.0, where we would like to go towards a more smarter, more monitored manufacturing of goods. There is, of course, transportation, smart cities and communities, where we would also like to embed sensors and know which facilities are used, for example, parking spaces in cities. And not only since the COVID-19 pandemic, logistics and retail companies have a vested interest in knowing where their goods are. And if you think about the initial shipments of the COVID-19 vaccine, we also need to monitor certain perishable goods for the duration of the transportation. And essentially, this is where these embedded devices come in. And as you can maybe tell, they are vastly different, but what unites them is essentially communication, because being an internet-connected device without communication is unfortunately fairly hard. And if we look a bit further into the requirements of these systems, they unfortunately are not easy to build. They have to operate autonomously for very long periods of time. So, for example, many of those systems are retrofitted and have to rely on batteries or even energy harvesting, drawing the energy from the environment around them. And even worse, why don't we just plug them into, well, Ethernet or power? Well, unfortunately, where these systems are often deployed, there is simply no infrastructure available. A great example that I always like to bring up is there is a sensor network actually deployed on the Matterhorn, so the glacier here in Europe. And if you can imagine the tremendous amount of money they had to spend to get the helicopters to deploy these sensors in hard-to-reach environments, getting a research grant essentially to replace the battery is not going to happen. And this brings me essentially to my next point, which is reliable and fault-tolerant operation. You have to consider that these systems are made out of many hundreds or thousands of devices operating together to fulfill a task. And of course, as such, it cannot be that if a single node fails, the entire system goes down. So the entire system has to be fault-tolerant to the failure of individual nodes. And looking back to the Matterhorn, these systems have to operate in harsh environments, not only harsh in the sense as it would be for a human, so extreme cold or heat, but also harsh in the sense of machines, so electromagnetic interference and other technologies communicating in the same frequency band interferes with the operation of our system. And well, the system have to survive that. And further, unfortunately, many of these use cases, while not imposing strict real-time requirements, so a guaranteed deadline, it is usually fundamental that they are able to operate reliably, so 99.79%, and with extremely low latency. If you think about a factory floor where I now have a wireless emergency stop, by the time I press this button, A, the message has to be delivered without fault, and B, it has to, of course, happen, well, better sooner than later before something terrible happens. And if you now think that thing might be battery operated, it would be terrible that the one time I press the button, the battery is essentially depleted. And This essentially is covered by a term which is called dependability. So these deeply embedded systems are usually dependable systems which have to satisfy many of these requirements. And even worse, since we operate on batteries or on harvested energy, we have low power. And since we don't have infrastructure, we typically have wireless devices. And while, of course, many telecom provider would like to convince you that 5G or even 6G in the future will be the solution to all of your problems, consider that unfortunately, the distance over which we communicate impacts the energy, and not in a linear way, but rather to the power of 3. So the further away you are, the massively more energy you have to spend. And as such, even if we had many more cell towers around, which are expensive to deploy and maintain, just the communication to this base station is very expensive in terms of energy. And this is essentially where the technology that I'm focusing on comes in, which are wireless meshes. So if you look at the picture here, you can see that not each node is connected to each other node, but using the other nodes essentially as infrastructure, we can relay messages from any point to any other point in the network. The great news is we don't have to deploy a separate infrastructure. We only need a couple of gateways, which essentially then take these low power messages and at some point translate it to the internet. Unfortunately, due to the low power constraints, we also have a low data rate. And we are now essentially splitting that data rate in our own data and the data that we are relaying for other nodes, which also imposes the requirements of routing over not only a low power, but also lossy network. So as you can imagine, with nodes occasionally failing, with nodes being mobile, or even worse, with the environment constantly changing, and some links suddenly becoming unavailable, our routing protocols also have to take care of that. And as such, we have now distributed systems with a high complexity, with many components, including communication. And of course, I don't think I have to tell you, the best thing we can do to figure out which one is now the best one is to employ benchmarking. And while I have been told in every other, or essentially every other domain, there are established benchmarks. If you try to search for a benchmark for low power wireless protocols or systems, you unfortunately have no such luck, or you had no such luck. Essentially, during my dissertation or my doctoral degree, I focused on the research question of how can we actually design and build a benchmark to evaluate and compare the performance of these low power wireless systems and protocols. And as such, I would like to start off with how we envision such a benchmark to work. And of course, you either go on the internet and find a lovely protocol on GitHub or wherever, or you are the actual author of a protocol and you would like to see how it performs against a state-of-the-art or another protocol. And as such, you essentially compile your software for a target platform, you send it to the the benchmarking facility, and after a while, the benchmarking facility will reply to you, these are your results. And since we are, let's say, nice researchers, we of course also store all of the artifacts. So if ever there is doubt or ever the environment changes, we can rerun those experiments because we kept the original binaries. And of course, we also store the results because while it is great that you now know how you compare against other protocols, we would like to have a public leaderboard where essentially the world can now compare also against your protocol. But as you can imagine, we have a bit of a problem here. Namely, when we design such a benchmark, we have to make a careful trade-off between generality and accuracy. For example, there is a somewhat famous tunnel in Trento, Italy, which is often used to test certain IoT systems, which has the task of measuring the light and the brightness at the entrance of the tunnel and relaying it throughout the tunnel via multiple hops so that the light inside the tunnel roughly matches the outside, so you don't go blind when you drive into it. And while we could now build the Trento tunnel bench, this would be very accurate for exactly one deployment. And of course, the other extreme is we strip away everything and just say, well, it's communication in low power wireless computing devices benchmark, which would have incredible generality and would apply to absolutely everything. but would be completely inaccurate for every possible outcome. And the benchmark's target essentially is to strike a trade-off in between those two. And if we now look at the reality of how it is done before we had the DQ benchmark, and how researchers have done it to this point. So we have researched for more than 20 years. There's a large body of work out there. So we take our protocol, we pick the recent publications, we find a protocol which aims to do roughly the same, and it turns out we're actually not that great. So we have two options to go forward. Either we fix our protocol, or unfortunately, we fix the problem. So we simply adapt the parameters, say maybe my protocol performs better when there are more nodes, or maybe I do better if, I don't know, I send data less frequently. And I repeat that, and at some point, I hopefully have the point where my protocol is better than whatever I found during my research. And as is tradition, I, of course, write a paper. I want to have a PhD. And so a new paper, a new protocol is born. And while this is very much not what I think happens, unfortunately, looking at the outcome, it might as well be. So key researchers in the field of low power wireless communication actually conducted a survey. They looked at 5 years of publications and at all systems supporting only periodic data collection. So a very narrow subset already of the general task of communication in low power wireless systems. We can see that only focusing on 2 parameters that are fairly important, namely how big was the test setup. So on how many nodes did they test their protocol, we can see it ranges from a few nodes that essentially can still fit on my desk to a test bed with the size of more than 100 nodes. And also terribly, the delay between individual messages. So not talking about their size, just how often do you send data in your experiment? It ranges from once a second or more than once a second, all the way up to 5 minutes. And what always hurts me a bit as a researcher is the size of the circles, because many researchers only ever publish one result, i.e. it worked once, while others use due diligence and actually report on, well, all of their results and how well their protocol performs essentially over multiple runs. And with these problems in mind, we actually designed DQ. So I built most of it, but I have to here acknowledge my supervisor, who was heavily involved in organizing many of the things. And the name of this benchmark is called DQ, and it's, to my knowledge, the first benchmark for low power wireless systems. And how you interact with it is fairly obvious in today's world. You have a web interface, you log onto the testbed, you upload your binary, it will be scheduled for execution. The testbed sets up the experiment, automatically performs the experiment and returns you the result. So you cannot essentially pick your parameters at random and find a point where you're better. It is the same for all of them. And what I have to, however, point out is that these variations were not made in malice. They are actually, as we had in the beginning, different use cases requiring different parameters still. And we modeled these as so-called benchmark suits, which is essentially an envelope where I say, well, it is a periodic data collection, for example, but as different applications or different use cases require different parameters, there is a list of parameters that can still be selected, for example, with the generation of traffic or with the node placement. So we don't physically move them, but we essentially change the identity of the source and destination nodes within the network. And to this end, we then take this data and inject it into the firmware via binary patching. So what happens is there is, if you think about C, there is a struct at a specific location in memory, which a testbed overrides, which the firmware at startup then can read and is aware that A, it is a source or a destination or a forwarder, and what kind of data does it have to expect essentially. And since we can use the one firmware for many different tests, we can actually benchmark a single firmware for a wide range of parameters. And of course, I can't talk about benchmarking without actually measuring something. there has to be a metric in place which tells me how well I performed. And if we think back to these dependable systems, essentially we want to answer the question, do the solutions allow for reliable, timely, and energy-efficient communication? And we express these three key questions as metrics: the reliability, that's the number of messages that were successfully delivered from one end of the mesh network to the other; the end-to-end latency, so not how fast you can relay from one hop to another or how many hops you need, but we only consider the end-to-end, obviously. And since this is a mesh network and I do not know which route you may or may not have taken, we have to consider the energy consumption of the entire network, because a node with a depleted energy is unfortunately not able to do anything at all. Good. So how do we actually, now that we've designed this benchmark, run it? I skipped over the testbed infrastructure box in my initial workflow. And actually, this testbed infrastructure is a box made out of many boxes, namely the box that you can see here in the picture, which is what we call an observer module. Its job is to actually be the physical manifestation. So it is the bridge between the target node running the firmware and the testbed orchestrating it. And to facilitate the energy consumption and measurement of the energy consumption, we have added a special add-on PCB, which we open sourced in 2017. And if we now highlight a bit the components, we can see that, as so often, at the bottom, there sits an off-the-shelf Raspberry Pi 3. Into it plugs this measurement PCB, which takes care of the time sync, the isolation of the target node, the communication between the Raspberry Pi and the target node, and also these measurements. And in any off-the-shelf target node that supports power and programming via USB, which at this point is essentially every target node out there almost. And a key importance, since we have to deploy this across, in our case, 2 floors with more than 50 nodes in our facility alone, they have to be easy to deploy. And so we rely on power over Ethernet. So a single Ethernet cable is plugged into one of those observer modules, and it's already up and running. And while the silicon shortage sure has hampered this prediction, when we initially designed it and built them, we could produce one of those boxes for less than 100 euros or for roughly 100 euros without the target node. However, if we think back about these harsh environments, I want to now focus a bit on what we do to test or benchmark these protocols under harsh environments. And the key focus of my work was the RF interference generation. So as you can imagine, or as I said, these systems share a single frequency band with many other devices. The most prominent one in today's world is probably Wi-Fi. So for example, the low power technology that we usually use for mesh is in the 2.4 gigahertz band, which just happens to be what Wi-Fi has commonly used. Now it is starting to move a bit towards the 5 gigahertz band and even 6, but many devices still operate on the 2.4 gigahertz band. And luckily, the Wi-Fi card that is already present on the Pi can be well modified. So the firmware is not validated by at the time of loading. So we could actually inject the interference model we would like to generate into the firmware itself and have the card autonomously and repeatably generate the same level of interference across experiments, and as such can benchmark protocols and solutions under the exact same settings in terms of RF environment. However, even the best tool, and I might be biased here a bit, is not able to subtract interference. So there is no such a thing as a negative Wi-Fi packet. I can only ever add to the level of interference. And as such, we once again take the existing Wi-Fi card, but instead of generating interference on some of the nodes, we essentially create a firmware which uses usually unused debug functionality in the card to monitor the RF environment and turning the Pi into a essentially free spectrum analyzer, which now allows me to observe if the level of interference I wanted to generate was actually present at the end of the experiment. And I can thus ensure that actually the experiment will run under the same settings. Has this ever been done? So now we have built the benchmark. Has it been used? Of course. Actually, the entire benchmark started out as an ad hoc installation for a dependability competition, co-located with the International Conference on Embedded Wireless Systems and Networks. And I'm happy to say that when we sent out the call, actually over the years, more than 50 partners from not only academia, but also industry have answered the call. And in the beginning, so have already spoiled it, we have actually repeated this competition for 4 years. And what in the beginning was, can you transmit a single bit of information, so an event across a mesh network from one node to another, of course, in the presence of harsh RF interference, has over the years evolved into a more complex pattern, including, for example, data dissemination, which is used to, for example, disseminate commands across a low power wireless network, like turn on the lights, but also data collection, which essentially turns the destination into a bottleneck where we collect sensor data from across many different devices. And if you now look at exemplary at the last one of these competitions, which was in 2019, the initial 2-hour hackathon of 2016 turned into a 2-month preparation phase, followed by 2 months of pure evaluation over a total of 720 different parameter sets, with more than 10 teams participating over 2 categories. So data collection and dissemination were essentially independent competitions. And if you now look a bit at the top here, you can see these parameters include things like the level of RF interference present. The category was data collection versus dissemination, different node layouts, meaning more challenging placement of source and destination nodes, and a wide variety of traffic ranging from aperiodic to periodic and different sizes. I'm happy to say that the data is now static and permanently available as a data set. Yeah, you can scan the QR code or go to it-testbed.graz.at/EWS in 2019. And maybe this can be of use to you in the future. As summarize, I think, or I hope I have convinced you that also benchmarking can be used in the domain of low power wireless protocols and systems, and that DCube has hopefully alleviated the problem of comparing protocols and systems under the exact same settings and environment. And thanks to the operation on binary only data, we are able to provide the baseline even against industrial protocols, which cannot be made available in the form of source code. And further than that, we have used it to compare the state-of-the-art protocols, not by downloading it, but by actually using the researchers which develop these protocols to push the performance of their protocols to the edge. And we not only opened the infrastructure DCube to the public, so it's ready to use for anyone that wants, but we have also now fully open sourced the entire software and hardware stack used to build the testbed so others can essentially replicate it. So thank you, and I hope there are questions.